In part 1, I explained how you can use the technique of embeddings to provide access to Llama to your custom dataset. In this part, I'll be explaining fine-tuning, which is quite a bit trickier as a technique. As with part 1, I'll aim to teach Llama the rules of touch rugby, a dataset that is quite sparse online and therefore not really in the base knowledge of the language model. Fine-tuning is really challenging. So let me start at a really high level and tell you what works and what doesn't work for fine-tuning, before then going into a little more detail around the steps that are required. Here's a formula that does work. Start off with a chat model like Llama 7b chat, then convert your dataset into a Q&A format. So if you have a long document, convert it into question and answer pairs. Then use that Q&A dataset to train your language model for more than 3 epochs. An epoch means sending the full dataset through the model for training. So you need to do that 3 times or more. We've covered what to do, so here's what to avoid. Avoid training a chat model with raw text. I've tried this many times, but the chat models are already tuned so that they respond nicely in a conversation format. And if you then just overlay the raw text from a document and try to use that for fine-tuning, it tends to mess up the model somewhat, and it's very difficult to get clean, structured responses. I also don't recommend training a base model. Base models aren't designed to respond nicely in conversation format, but that's really what you need for any business application. If you do train that base model, you're going to have to further fine-tune the model so that it can provide this conversation style format. And that can be tricky in itself. And that's why models like Llama are provided with the chat format. So if possible, I would say stick to fine-tuning the chat format. But maybe somewhat unfortunately, if you want to fine-tune a chat format, it's best if you can get your data set into question and answer pairs. So here's what I'll cover in today's video. I'll explain the difference between chat and base models. Then I'll explain the difference between supervised and unsupervised fine-tuning. Supervised fine-tuning is what we'll use when we have question and answer data sets, and that's what allows us to get good performance and make sure the model is learning the content we're feeding in. Then I'll go through a specific example and demo of converting your data set into question and answer format. I'll provide a demo of supervised fine-tuning in a colab notebook, and I'll finish things off with some pro tips to make sure your fine-tuning is embedding knowledge into the model. I want to help you understand the difference between a base model and a chat model. Here in the Meta Llama repository, you can see an index of models. There's a base model of 3 different sizes, and there are also the chat models of 3 different sizes. Now note there are also these -HF models. That stands for Hugging Face, and these are the models that are easily compatible with the transformers library that we often use. So let me show you a demo of how the base model performs versus the chat model, starting actually with the chat model. I'm running Llama Chat here in Google Colab, and I've got a chat style set up. So let's ask some questions and ask questions that are related to our task today of training Llama on the touch rugby rule set. Let's start with how many players are allowed on the field in touch rugby for each team. And let's see what Llama Chat comes up with. So here we have an answer, and you can see that it looks like a reasonably structured answer. It's not the correct answer because Llama is not familiar with rugby. Let's ask another question. How long are touch rugby games? Give a brief answer. All right, so again, this is not correct in terms of answer, but it is well structured. Let's compare that now to the base Llama model and see how it performs. Okay, here's the base model loaded up. So let's ask some of the same questions. How many players allowed per team on the field in touch rugby? And let's just say provide a short answer, and I'll click send. So remember, this is the base model. It's not fine-tuned for conversation. And I just want to show what happens to the output that's generated. Now, this is not operating in streaming mode, so the answer will only display when it's being fully generated. And I suspect, yeah, so here we go. So first of all, you can see that Llama base is just responding with this, what looks like gibberish. And the reason is because I've provided the same prompt structure as though I'm using the Llama chat model, which doesn't work because it's not familiar with the chat type interface. I'm going to go up here in the code and I'm going to comment out the system message. Now, you won't follow all the steps I'm doing exactly, although I'll put a link in the colab notebook so you can follow along if you want to. Basically, I'm taking out the system message and I'm going to simplify what the fine-tuned structure is. So here we'll comment out the system message, or you can just ignore it. And for the beginning of the instruction, we're going to change this just to question. And for the end of the instruction, we're going to change this to answer. And see if this helps as a format. Okay, so we'll do runtime, run after, and that should run quickly. So here we are. How many players on the field in touch rugby? Let's see what it comes up with. And here's what we get. We have asked a question and now we are getting a reasonable answer, but you can see that the response is continuing and moving into another question, which is the same question that we asked, and then giving another answer and responding infinitely. And so these base models, they don't know two things. They don't know how to stop, and they don't know what style of answer and what kind of length that we're expecting if we ask a question. So the key takeaway here is that if you want to use a model for a business purpose, you probably want to start with a chat model and you want to fine tune that. You probably don't want to start with a base model unless you're willing to not just fine tune the base model, but then yourself manually through fine tuning, convert it into a chat model, which is not straightforward. I think now you can see the difference between the chat and base models and why it's valuable to start off with the chat model if possible. Next up, I want to explain supervised versus unsupervised learning. In supervised learning, you're basically giving a question and an answer, and you're seeing what the predicted answer is compared to the actual answer. In unsupervised learning, you're simply passing in a train of text, and you're always predicting the next token. And then you compare it to what the actual next token is in that string of text. So let's dive in a little more detail. It's an example of unsupervised fine learning. We have a phrase here, the wheels on the bus, and we're going to feed this into the language model and see how it performs. Now, there are two concepts that I want to explain here. The first is attention, and the second is loss mask. Each of these are matrices of ones or zeros. Let's start with attention. So we feed in this phrase here. Let's say we just feed in the wheels on the. So we feed in those 4 words, and we're trying to get the model to predict the next word, which should be bus right here. Now, what attention does is it says whether or not we're allowing the model to see the previous words. So when we're on the word the, having fed in the wheels on the, we set the attention mask to 1 for all of the previous words. So there'll be a 1 for the, wheels on. Now, actually, when we feed in the 4 first words, we won't allow it to see the word bus. So this would be a 0. Although then when we feed in the first 5 words and predict the word after bus, then we would allow the model to see all 5 of these words. So attention tells us what words were in the past usually we're allowing the model to see. Now, the loss mask tells the model what we're going to penalize it for. So if we set the loss mask to 1 here, we're going to say, okay, model, predict the next word after the, which is wheels. And based on your prediction, we're going to penalize the model or not and make an adjustment. Then we'll feed in the wheels and ask for a prediction of the next word. And again, we'll penalize based on the model's prediction of the word on. Likewise, the wheels on, when we feed that in, we're asking for prediction of the word the, and the loss mask is 1, so we're going to penalize based on prediction of the word the. So in unsupervised fine-tuning, you're feeding in a phrase, you're always allowing the model to pay attention to what's to the left, or the historical tokens, and you're always penalizing the model based on its prediction of the next token. So this may not make sense, but it will make a lot of sense when we move now to supervised fine-tuning. So here in supervised fine-tuning, we have a question, how are you? And we have an answer, I am well. And you'll see here with the attention mask, we'll feed in just how are you? And we'll allow the model to see all of these words. So we'll set the attention mask to 1s. However, for the loss mask, we're not going to penalize the model or ask it to predict the answer to the following token after how are, or you. So you can see there are zeros here. We're only going to ask the model or penalize it based on its predictions after the question. So what we're doing is we're focusing the model's training so that it is being adjusted based on its performance on the question. Its performance is not being graded, and the model is not being adjusted based on predicting next words in the question. It's only being graded based on the answer here. So you can see the loss mask is 1 for the word you, because we are going to penalize based on its prediction of the word after you, which is I. We are going to penalize and measure performance based on its prediction after the word I, which would be am, the same for am, which is well. And then there's this extra token we'll add in, which is an end of sequence token /s. So when the model sees all of the words, how are you, I am well, we'll ask it to predict the next token. And what we're going to expect is this end of sequence token. And this is the way that we stop the model from blabbing on. We train it so that if it should really be predicting an end of sequence token after well, and then when we run predictions later, say you're using it in a business application, we can simply detect that there's an end token, and that's how we know to stop generation. So just to go back, in unsupervised learning, we're penalizing based on every new token that's generated, whereas in supervised learning, we're penalizing only based on an answer and the performance on the answer, as well as on this extra end of sequence token. One of the practical implications here is that unsupervised fine-tuning is easier to do because you simply feed in a long stream of text. It's unsupervised because you always have a next token and the model always searches for the next token. In supervised fine-tuning, you need to split your data set into questions and answers because you need a split between what you're not going to penalize the model on and what you are going to penalize the model on. And that's what makes it supervised. Because the chat models are already fine-tuned for chats, they're basically fine-tuned for these question-answer pairs. And so if you want to fine-tune a chat model, you also need to have your data in these question-answer pairs. And that means if you just have a document like the rules of tag or touch rugby, you first need to convert that document into a set of questions and answers so you can do this supervised fine-tuning. Whereas if you started with the base model, you could just do unsupervised fine-tuning and you could push the full rule set of touch rugby through. However, that's not going to be enough for good business performance because, as we saw earlier, base models will tend to blab on and they won't provide answers in a format that humans will expect. Before I move on, I want to show you a small practical example of this in Google Colab and show you how the loss mask is set and how the attention mask is set. Here I am in Google Colab with a script that I will be talking through in much more detail later. But I want to show you one sample here. We have the following question and answer pair. So here we have a question. In the context of Touch Rugby International, playing rules 2020, what is the purpose of the advantage term? Okay, so this is the question. And notice that this is written out in tokens. So you can see the way I have this printed, everything has been tokenized. So interestingly, international is 1 token, but playing is split into 2 tokens. And then we have the answer. The term advantage refers to the opportunity for the non-offending team to gain territorial, tactical, or scoring benefits after an infringement. After an infringement. And notice how after the answer we have these padding tokens. These padding tokens tell the language model to ignore these tokens because they're simply there to add up space if we have a constant sequence length for all of our batches. Okay, so this is a question and answer pair. And what I want to show you now is the attention mask and the loss mask. So let's move back here. And we have the labels, the attention mask, and the loss mask. So the labels in this case are the correct outputs, and they're simply one shifted from the inputs. So said differently, if I have, say, the word what, the next word here is. So the label for the input what is going to be is. Basically, I'm saying to the language model, if you see an input of what and you see everything before it, you should be predicting is. If you see an input of is and what and everything before it, you should be predicting the. So the way that we get what the correct output should be is simply by shifting the inputs 1 to the left. And that's true in supervised or unsupervised learning. Next, we see the attention mask, which says to the model, okay, we're going to allow you to see all of these tokens with ones. And you'll notice that the attention mask is all ones because we're always allowing the model to see what's to the left, but it ends. And the reason why it ends and goes to zeros is because we hit the padding tokens. So in the input sequence here, once we get to the end of the answer, we have these padding tokens, and we never want the model to pay attention to the padding tokens because that's a waste of computation and also not useful information. So if you went through the numbers, you would see that once we get to the end of the tokens, we'll move to zeros for the padding token. Now, next we have the loss mask, which tells the model what it's going to be penalized on. And remember, for supervised fine-tuning, we're not going to penalize based on predicting tokens in the question. We're just going to penalize based on predicting tokens in the answer. And that's why it starts with zeros, because the prompt starts with the question. So there's all zeros, and then we move to a point where we have ones. And this sequence of ones here is exactly the same length in tokens as the answer. And this tells the model during the backpropagation phase and calculation of the loss that we're only going to consider the losses on predicting these tokens in the answer. Now you'll notice this then moves to zeros. And again, that's because of padding tokens. Once we get to the end of the answer, we have padding tokens. And of course, we're not going to grade the model. We're not going to consider any losses on predicting padding tokens because that's not, it's not a useful part of the prompt. It's a waste of computation and would also confuse the model. So the key point here is that if you're working with supervised fine-tuning, you need to have a loss mask. You need to focus the losses or the penalization of the model on the answer only and not on the question. Whereas if you're doing unsupervised, then you're penalizing the model based on every single token. And again, because we are using chat models, which are already fine-tuned for this chat format, we want to fine-tune them using a loss mask. We want to fine-tune them where we penalize only based on predictions of the answer. So I see two high-level approaches that will work for fine-tuning. The first is you can fine-tune a chat model, which is what we're going to do today, in a supervised way. And for this, you'll need a question and answer data set. The other approach you can take is you can fine-tune a base model using unsupervised learning, which is easier to set up because you don't need the Q&A data set. However, you will still need to get your model into a conversational style. And for that, you would anyway have to do some supervised fine-tuning. Otherwise, you'll get verbose answers or uncontrolled answers. So let's take things step by step. I'm going to start by explaining how you convert a document into a question and answer data set. I'll do that just using ChatGPT, and then I'll do it using some scripts from GitHub. And then I'll take you step by step through the supervised fine tuning and show you the kind of results we get on teaching Llama about touch rugby. All of the scripts are available in a private repo for purchase. It's called Llama Fine Tuning. You'll find scripts to train for function calling, for supervised fine tuning, and also for the embeddings approach that was covered in the video from last week. I'll also explain everything at a high level, so you should be able to follow along and replicate. Just ask in the comments if you have any questions. Now, I've opened up the repo in VS Code and I'm on the supervised fine tuning branch. You can see here the PDF I'm going to use for fine tuning, which are the international playing rules of touch rugby. And this is a PDF that has about 24 pages. I've run a script which is PDF to text, and I've converted that into a text data set, which is this one right here. Here's the raw training data. It's simply the PDF converted into text. Now, what I want to do is convert this raw data set into a set of questions and answers. I can show you a little bit what that looks like here because I have a training data set. So I want a set that's got a prompt and a completion, something like this in the context of touch rugby and the international playing rules. Who led the internal review of domestic playing rules? And then the answer, touch rugby Australia. So to get into this question and answer format, I'm going to make use of another language model. I'll show you here using OpenAI and the API, but you could also use Llama as well if you wanted. The easiest way for me to explain how to convert your data into a Q&A data set is with ChatGPT. I've got a snippet that I just copied from the raw text in the PDF. And what I'm going to do now is provide a prompt after that text. So here's a little snippet that I have for the prompt. And the snippet is provide X questions and answers based on the text above. I'm going to just say provide 5 questions and answers based on the text above. The questions must begin with in the context of. The answer should borrow verbatim from the text above. Vary the style and format of questions. Respond in plain text on a new line for each question and answer. Leave out the question numbers and bullets. And here is a sample question and answer. And I'm just going to paste in a sample question and answer right there. And here we go. So notice a few things about this prompt. First off, I'm making sure that the question has the context. If you just train a language model on some random question like, what did Rule 3 say? It's not going to know what Rule 3 refers to. So it's important that every question has the context of the answer. The other thing is I don't want the language model to hallucinate and give answers that are wrong, which is why I'm saying the answer should borrow verbatim from the text above. I do want some variance in the style and format to get some better fine-tuning, so that's why I include that. And the reason why I ask for a response in plain text on a new line is because I'm then going to take the file with these questions and answers and convert them into a Hugging Face data format. So let's just run this query here, and we'll see the answer that we get out. So here we have a first question. Remember, we've asked for 5. Here we have a second question. Now, this is not great, so you will see some imperfections in the questions because it's saying in the context of these rules. Here, the context is correct. And here's another one. Now, you can improve even further if you want on that prompt. For example, you can adjust here, and let's just say, here, vary the style and format of each question. The answer should borrow it verbatim. Let's add a snippet here that says, in providing each question, consider that the reader does not see or have access to any of the other questions for context. So let's try that. So here you can see now that the context is even better. And we have our 5 questions. Before we move on, I also want to show you how you can create a validation or test data set. So we have a training data set, but we also want a data set that will track the progress during the training. Ideally, it should cover the same content, but the phrasing should be different so we know if the model is overfitting to the training data or not. To do that, one little tweak we can make here is we can simply ask for fewer questions because it's going to be a shorter data set for evaluation than for training. And rather than asking the answers to borrow verbatim from the text above, we can say the answers should not borrow verbatim from the text above. And what this does is it's going to give some variance to the answers that are being provided. So we can just save and submit. So now the answer portion to each question is going to be a little bit more varied compared to what we had in the first set where it was borrowing verbatim. And this gives us a nice data set that can be used for evaluation. Okay, we're back here in Visual Studio, and I'm going to show you how we can automate all of those steps to generate Q&A from a given data set. So first off, I've got my raw training data, which is literally the text scraped from the PDF. And what I want to do is convert that into a list of questions and answers. So I'm going to run Python, and I'll run create qa.py. Okay. Now this script is set up so that it tells us how many tokens are in all of the chunks of text, which is 10,000. It will tell us the estimated cost of doing the chunking and question generation with GPT-4 and also with GPT 3.5 Turbo. So it's going to cost about 11 cents. Now in the script, which is create Q&A, I've already set to use 3.5 Turbo. Let's just check where that's set. Here we are. You can comment in GPT 3.4 for a better quality Q&A. And now the script is asking me whether I want to process just one chunk, which is the first of all of the chunks. It needs to be chunked because they won't all fit in the context length of GPT. So I'm just going to, for this demo, process one chunk, which is a portion of the text. It'll be faster. If you process one chunk, it'll print to console what the chunk is and what the prompt is, so you can verify that. So that request has now gone over to GPT. And what's going to come back is a data set which will be printed into train.txt and also printed into text.txt. This can take a little bit of time if you're generating Q&A for a long document. I'm just doing it for one chunk of this document, which is already not that long. It's 24 pages. So we should get an answer any moment. And it's just printed here. So you can see we have a series of questions. So we've got roughly about 25 questions. And in test.txt, we have 2 test questions. Note also that you can generate more questions for a given amount of text if you want to have more training data for the model. You can tweak that within the code by lowering the number of tokens per question. So what this says is for every 25 tokens in the raw data set, give me one question. If I instead set it to for every 10 tokens in the data set, give me one question, that's going to generate even more questions. So one of the levers you have here is you can generate more questions for a given data set length, and that will allow you to have a better fine tuning. Okay, so we have our data in that format we want, which is question answer space, question answer space. And now we'll run a script that should allow us to convert that data into a CSV format. So I'll run Python and I'll run QA to CSV.py. And what that's going to do, and it'll be very quick, is just convert what we had in those rows into the correct format for a Hugging Face data set. So here now you just have everything in prompt completion format we have those 27, well, it's actually 27 and minus top row, 26 questions. We've the question and the answer, and also for the test data set, we've the question and the answer. Now, the last step I'm going to do is I'm going to push that data set to Hugging Face. So I'm going to do Python push to hf.py, and it's now going to ask me for my access token to Hugging Face, and it will then ask me for the repository that I want to push the data to. And then it's going to push the test CSV, the train CSV, and also a README file, which is in the data folder, up to Hugging Face so that you have a full data set ready. All right, now that we have our data set ready, we're going to use it for some supervised fine tuning. I'm back in the Llama repo, and I'm downloading this fine tuning notebook and opening it up in Google Colab. Now, it should be possible to run this on a free T4 GPU. The first step is to connect to Hugging Face Hub. So you'll run that cell and enter your token to connect. I recommend connecting to Google Drive. It means that you only have to download the model once, and it'll be quicker to download the next time. And then you run the installation. Next, you want to load the model. As we discussed, we're going to fine tune a chat model, not a base model. You can fine tune a 7B or a 13B in a free Colab notebook. Obviously, the larger the model, the better the quality of fine tuning you're going to get. I went with the 13B because it's the highest quality model I can run in a free Colab notebook. Note that I'm loading it in quantized form. That allows it to fit in a smaller GPU and also speeds up the training. The next step is we're going to load some LoRa adapters. So rather than fine tuning all of the weights, we're going to fine tune an adapter, which is basically a set of copy-paste weights that are applied to the main model. But that set of adapter weights is a much reduced matrix. So it's actually two smaller matrices that together are multiplied to give a matrix that fits onto the main model. This is a common technique called low rank adapters. So we load the low rank adapters. We're going to train all of the possible modules. It's common sometimes to just train the K and V attention, but since we can train more, I find that training more works quite well. We'll then set up the tokenizer and the padding. Now, a few things you'll recognize from earlier in the video. We have to set a pad token. This is because we're going to send the data through the model. We'll send the question and answers through in batches of 8, and we need them all to have the same length. So where there are shorter questions and answers, they need to be padded out using the pad token. We're going to pad on the right-hand side, so all the padding will appear to the right-hand side. And we need to configure the model's pad token to also be that specific pad token. Okay, so as if you watched the embeddings video, you'll see that we now set up evaluation. And this is a set of curated questions that I've made manually. I definitely recommend you do this. It takes extra work to do anything manually, but just set up even 10 questions and then set up 10 answers based on your data set and just make them up yourself using the old head. It's a really good way to measure actual performance. We do have an evaluation data set, and you'll see that allows us to track nicely the training progress, but ultimately it's the quality of answers that you get out that matters. So I really recommend putting together some test questions and answers. Now you can run the evaluation. So here you can see how does the game commence. I'm just running on the raw model here. There's no fine tuning. So the model thinks the game commences with a kickoff, which is incorrect. It actually begins with a tap on the halfway line. Here's another question. How many meters must the defenders retreat when there's a penalty? It's 10. It's probably getting that right because in rugby it's also 10. So this is important. Run evaluation. I can tell you that out of the 10 test questions, raw Llama gets about 1 or 2 correct, depending on the size of model you use. And I think the answers it gets are probably fluke because they overlap a bit with normal rugby. You can see it thinks a try is worth 5 points, which is true in normal rugby, but in touch rugby, it's only worth 1 point. Okay, next up, we'll load the data set that we had pushed to Hugging Face. Now, there is an important point here, which is you need to set the data length. So you remember I said we will send the data in batches of 8. Well, we need to set the batch length, and it needs to be longer than the longest row that we have. And an easy way to know this is just check the script. So actually, if I scroll up to where I made the CSV, I can see here that the maximum number of tokens in a row is 85, and here it's 59. So for this data set, which is a smaller data set, I would need to set it maybe to about 100. When I ran that script over the whole document, it generated many, many more questions. And so the longest data, I think, was maybe 150. So for safety, I'm setting the data to about 180. Notice that, well, not notice, but know that if you set it longer, that means you're sending more tokens to the model. So it will take up more memory and time for training. Of course, if you set it too short, it's going to truncate your data, which you don't want. So do set it with a little bit of headroom. All right, so now we're going to load this data set from Touch Rugby Rules. We can check out, if you like, on just Hugging Face. We can just look up here, data sets and Trellis, and see here a data set I pushed earlier, which has 227 rows, and it has 100 test rows. So here you have the prompt and the completion. So that's the data set we're loading. You can print out some tests of those data samples. So here's a test. Here's a sample from the training set. Here's a sample from the test set. Now, next up, we need to organize the data set. And you'll remember we talked earlier about setting the loss mask and setting the attention mask. We need to set the loss mask on the answer. We want to penalize the model based on its predictions of the answers, not based on the prediction of the questions. And this is where we're going to come back to the little example I showed you when we examined the data sets. You'll remember just a few minutes back in the video, I showed you one of the examples where we have a tokenized input. Then the correct answers that we're expecting are the labels, which are just the inputs shifted one to the left. Then we have the attention mask, which tells the model what to pay attention to, and critically tells the model to ignore the pad tokens at the end. That's why it's zeros. And then we have the loss mask, which tells the model to pay attention to the answer, but not pay attention to the question and not pay attention to the pad tokens. Okay, moving on, we can move to the training. Now, you'll remember right at the start of the video, I recommended training for 3 epochs or more. An epoch means a full run through the data set. Every time you run through the data set, it will move the model to fit your data a little bit more. And so every time you run through another epoch, the model starts to fit your data more and more. And if you do it too much, then your model will exactly fit your training data, but it will fit that exact phrasing. And so it's overfitting, and it's not going to generalize well to many questions. So there's this balance between, if you don't train for enough epochs, it's not going to know the data you have, but if you train for too many epochs, it's going to overfit. And I think somewhere around 3, 4, 5, 6, it's probably a big range, is where you want to train for those epochs. Now, this script has been set up so that it will save in Google Drive a copy of the adapter at every 4 training steps. So you can save basically a copy of the progress as you go along, and it will also save the data. So here we have our custom supervised trainer. This is written so that it only penalizes the model for predicting the answers, not the questions. It will do some logging of the data to a log file. And let's move on down here through the code to the point where we run the trainer itself. So just a few comments here. You'll remember I said we're going to run with a batch size of 8. That will just fit in memory if we're using Llama 13B. If you're using Llama 7B, you can fit 16. If you're running on a larger GPU like an A100, you could fit an even larger batch size. If you find that you run out of CUDA memory, then you can reduce your batch size. So I've set the eval batch size to 8 as well. We're going to update and backpropagate after every batch, and we're not going to accumulate gradients. Accumulating gradients basically says, all right, let's train with this batch, calculate the loss. let's calculate the loss from the next batch, then kind of average those losses and then update the weights. This can be good because it saves time and it gets some nice averaging so that you avoid some noise. But we already have a batch size of 8, so I feel like we can just have no gradient accumulation and actually run the backward pass after every forward pass. I've set the learning rate to 3e minus 5. This is a bit lower than what I see online. Yeah, so the learning rate here is a little bit lower, and I think it allows the training to be a bit more stable. There's a technical note that when we're using LoRa adapters, we're using a rank of 8 and we're using a LoRa alpha of 32. The ratio there is 4. So when you have a LoRa alpha that's higher than your rank, which is 4 times higher, it's actually accelerating the training by a factor of 4. So even though it looks like we're using 3e minus 5, because of the LoRa configuration, we're really using 4 times that. So we're really using 1.2e minus 4, which is a higher training rate than it looks like on the surface. Okay, I don't really have any other comments here. We're going to use a constant learning rate. So the risk with a constant learning rate is that you're trying to push the model to learn at the same rate as you push more and more information. And once the model does get trained, that can lead to more instability. Sometimes you might use cosine, which will decay the learning rate. So that's something you can play with. If you wanted, you could swap this to cosine, and you could use maybe more epochs, maybe use 8 epochs with cosine decay, which will give you fast training at the start and then kind of smooth down the learning rate as you go. Okay, so then we're going to run training. And you can see that we're logging the training loss and the validation loss. So this is our training data set, and this is our test data set. And you can see that training and validation, they're kind of tracking each other initially. And then over time, actually, the validation will stop tracking. You can see that in nice plot format here. So we have the training loss versus the number of steps and the eval loss. So you can see that the training is progressing nicely. But when you get to about here, this is about 1 epoch. So the model has seen the data, all the data once. The eval loss is now going to slow down and it's not going to reduce as quickly. And this is because the training is making the model fit the data more closely. But because the eval data is phrased differently, it's not going to have the same benefit for that. Now, what I find empirically is that you would think, well, maybe you should stop if the eval loss is breaking away from the training loss. That's probably somewhat true. But actually for these fine tunings, I think you probably want to overtrain a little bit to make sure you embed the knowledge. So actually you'll find performance gets better, even if you overtrain and you have some divergence. Now, if you see your eval loss start to rise, that's definitely a bad sign and you probably need to stop. You probably don't have enough data, or you probably have too high of a learning rate. So then you can run some evaluations. I'm going to run some evaluations at 20 steps, 40 steps, 60, 80. So this is about, I think, 0.7 epochs, 1.4 epochs, 2 epochs, and then just about 3 epochs here. And you'll see that after about 20 steps, you need to know the questions here, but this is ultimately the right benchmark. After about 20 steps of training, you don't see too much improvement. You see the number of players in the field is still wrong. Forward pass is a scrum, which is wrong. So we're not seeing that much improvement after just 20 steps or just under 1 epoch of training. You can see a change here. This previously was answering 10 meters. Now it's 5. So it's still wrong, but it's changed. And it's wrong. It's saying there's no substitutions allowed. Now, if you move on and you go to about 1.4 epochs, checkpoint 40, things are starting to improve a little bit. We're starting to get the correct number of meters for retreat. And if you move on even further to 6, which is 2.2 epochs roughly, so checkpoint 60, about 2 epochs, we're now starting to get even more questions correct. So you can see that it's still getting the number of players wrong. It's getting the roll ball wrong. It's getting the number of meters correct, but now it knows there's unlimited substitutions allowed. So this is good. It's getting half time correct. The game commences with a tap. And as you move all the way out to the very last checkpoint here, which is 3 epochs, at this point, I think the model is getting roughly about 7 of the questions correct. It's even recognizing there's 6 players on the field. It's not getting this question. This is a difficult question, though, because I've misled it in the question here to think it's one of these options, but actually it's something else, which is a penalty. I think the problem here is that the model is simply not big enough to be able to get this right. It's getting many of these correct here, starting with a tap. The penalty it's getting incorrect. That's also kind of a tricky question because in touch rugby, it can be 7 or 10 meters, depending on the exact circumstance. I think, again, a stronger model would probably get that right. It gets the 6 touches. That's correct. And it gets a try is worth 1 point. This question here about what happens if a player is touched by an opponent prior to making a pass, it's actually a rule that's not explicitly described. You kind of have to fit it together from different parts of the rule book. So that's a real tester. Even GPT-4, when given the full rule book, doesn't necessarily get that one right, as you can find in the embeddings video. So what you can see here is that a few things are helping us a lot with the performance. It's nice to have an evaluation data set. It allows us to track progress. We know that because this isn't spiking back up, our training probably went well. But ultimately for performance, you need to check out the examples to see if the training is going properly. And here are those pro tips. First of all, make the context clear in the question when you're making your Q&A data set. If you have a question that says, what happens in question 3, that's not giving any information to the language model to help it predict the exact answer. Second, increase your batch size until you're running out of VRAM. When running in a free collab notebook with Llama 13B and with samples up to about 256 in context length, you can run about a batch size of 8. If you run Llama 7B, you can run with even larger batches. But if the batches are too large, you'll run out of memory. If you want to improve quality and you're not getting your fine-tuning where you want it to be, you can consider generating more question and answer pairs. You can do that using the script in the repo by having the number of questions per token or the number of tokens per question generated reduced in the script, which will give you more questions for a given number of tokens in your original data set. Also, stands to reason that using a more powerful model for generating Q&A might give you better quality questions and answers, and that also can improve your fine-tuning. Last of all, remember that there's a limit on how you can use OpenAI. You cannot use it if you're training competitive models. So if you consider the model you're training to be competitive with OpenAI's models, then you probably want to use something like Llama 70B for question and answer generation. However, Llama 70B itself is only allowed to be used for training Llama models. So if you want to train Llama, you can use Llama to generate Q&A, but if you're training some non-Llama model, then you might have to use something like Falcon or MPT to generate your Q&A data set. Just want access to the supervised fine-tuning notebook, you can purchase that on its own, or you can get access to the full GitHub repo that has scripts for preparing your Q&A dataset. It also gives you access to scripts for fine-tuning, for function calling, for supervised learning, for unsupervised learning, and even for the embeddings video of last week. That's it for this video, folks. Cheers.